Welcome back. Today's lecture is going to be very similar to what we've talked about already, but we didn't discuss it using complex numbers. So let's focus on complex numbers today. I've mentioned this before, that if you multiply two complex conjugates, so let's review complex conjugate. If you have a number a plus bi, complex number, the conjugate is a minus bi. Exactly the same values, but the opposite sign for the imaginary part. The real part is the same, imaginary parts are opposite. So for example, 1 minus 3i and 1 plus 3i are complex conjugates of each other. What is the property? The property is that if you multiply complex conjugates, a minus bi multiplied by a plus bi, and if you distribute, go through the process, what do you get at the end is a squared plus b squared. So what do you get at the end? There is no imaginary part. Everything is a real value. For example, if you multiply 1 minus 3i by 1 plus 3i, what you get is 1 squared plus 3 squared, which is simply 10. So if you distribute, the complex parts will cancel out and the imaginary part will cancel out and the real values will add up together. Okay, this we have mentioned it before, but last time I mentioned that if you multiply, let's say something like, if you remember the factors form, so let's say if you have x minus 1 times x minus 2 for a polynomial f of x or y equals to that, we know that two zeros are 1 and x equal to 2. But we never mentioned that what if the zeros of a polynomial are complex numbers. What you do is exactly the same thing. You say, okay, I'm going to write x minus f of x would be x minus c1 times x minus c2, and so on. You multiply all the solutions, c1, c2, up to cn. Let's say there are n solutions. So what if these zeros are complex numbers? What happens? The result, still, we want it to be a real coefficient. There shouldn't be any complex number, but we want to discuss how you multiply. Is there a faster way to multiply or something like that? So let's assume that you have x minus a plus bi, and you multiply by x minus a minus bi. So I'm multiplying two terms that are conjugates of each other. These two are conjugates of each other. And what does it tell me? That tells me if I have a function f of x with these two solutions, the solutions are x equals a plus bi and a minus bi. The two solutions are conjugates of each other. What do I get if I multiply these two? Do I get a real coefficient for the polynomial or not? So let's distribute and see what do we get. X times x, x squared. X times the other parentheses, you can distribute it or you can write it like this. Minus a, I'm going to maybe distribute later. So here, a minus bi times x. How about this parentheses times x? I'll get minus a plus bi x, and this parentheses times the other. Negative times negative becomes positive, and what do I have is a minus bi times a plus bi. This is if I multiply the terms together. Let me erase this part. Okay, let's simplify it a bit more. X squared is still there. I have negative ax. I'm going to do this. Negative ax minus would be plus bix minus ax again and minus bix. Okay, now you will see that these two will cancel out because they're opposite of each other. And what you have is, if you distribute this a minus bi times a plus bi, we already did that. What you get is a squared plus b squared. So at the end you would have plus a squared plus b squared. And let me rewrite it here. X squared minus ax minus x, you get minus 2ax, and plus a squared plus b squared. What do we get at the end? There is no imaginary part. Everything is real value. So if you have a polynomial with real value solution coefficients, it turns out that if you multiply two complex conjugate solutions, the result still becomes with real coefficients. There is no complex coefficient. There is no imaginary coefficient. And there is a shortcut. You don't need to go through these distribution. If you have these two terms multiplied by each other, simply the result is x squared minus 2ax plus a squared plus b squared. I'll show you an example. Here, for example, let's say if they give you x minus 1 plus square root of 3i times x minus 1 minus, you want them to be complex conjugates of each other, 1 minus square root of 3i. So this is a plus bi, a minus bi. If you multiply these two, what you get is the product. Let me simplify. Using this format, I'll get x squared 2ax. This is a. I'll get minus 2 times 1 times x plus a squared, which is 1 squared. B squared is square root of 3 is b. So plus square root of 3 squared. If you go through the distributing, you still get the same result. So this is just a shortcut to the procedure. So you'll get x squared minus 2x plus 1 plus 3. Simply x squared minus 2x plus 4. Now, if I ask you, find the solution to this equation, x squared minus 2x plus 4 equal to 0. I ask you to find out the zeros of this equation, solution to this equation. What do you get is x equals, you'll get two solutions. One is 1 plus root 3i. The other one is 1 minus root 3i. You get exactly these two solutions. That's what you expect. So now you're given the solution, the zeros, and what they want is the polynomial. That's why we went through distribution. That's why I wanted to discuss this before we get into that multiplication later on. So I'm going to use this shortcut later to multiply. Okay. Finding a polynomial with given zeros. We've already discussed this for real values. So for example, given x equal 1 minus root 2i and 1 plus root 2i as zeros of a polynomial, as zeros of f of x, find f of x. And let's assume f of x is a second degree polynomial. F of x is second degree polynomial. With leading coefficient term 1. So what do we get is f of x equals, remember, if they don't tell you the leading coefficient, you have option to pick for leading coefficient. So leading coefficient was this a times x minus the solution, 1 minus root 2i. That is one of the solution. And the other one is x minus the other solution, which is 1 plus root 2i. This leading coefficient a is optional unless they give you an extra information. In this case, they tell you, let's say, for example, pick this leading coefficient to be 1. So don't put any number there. 1 times. So if you multiply these two, what do you get? I'm going to go through the shortcut. X squared minus 2 times a, this is a, that is b. You'll get 2 times a, 2x, 2ax, and plus a squared, which is 1, b squared is root 2 squared, which is 2. What you get is x squared minus 2x plus 3. And I found the polynomial. Here, it is important to know one thing. This is a very important note. If you have a solution in terms of complex number for a polynomial with real coefficient, so if a minus bi is a solution, a plus bi or a minus bi is a zero of a polynomial. Polynomial with what? With the real coefficients. Real coefficients. What does it mean? That means at the end, when you multiply all these numbers as a coefficient, they're real values. There is no complex numbers. So if you have such a polynomial with a real coefficient, what are the zeros? If one of them is a plus bi, the other one, then the other one has to be the conjugate. A minus pi is a zero as well. So if I tell you, for example, in the last example, if I tell you 1 minus b root 2i is a zero, just by knowing that the polynomial has real coefficient, you should say the other zero is 1 plus root 2i. The polynomial may be higher degree polynomial, maybe 5th order, 6th order degree polynomial. That means you would have more solutions, but you know at least 2 of them. Just by knowing one complex solution, you should know the other one. Okay, let's use this in one example here. As an example. Given, let me change this. Given x equal to -1 and 1 minus I as zeros of f, find f of x. And let's assume f is third degree polynomial. Okay. If I tell you that f is second degree polynomial, then product of x minus 1 and x times 1 minus I, x minus 1 minus I, if you multiply the coefficient would not be a real value coefficient. So at least I need a third degree polynomial. Just by giving these two and knowing that one of the solution is imaginary number, complex number, I can say the conjugate of that, which is 1 plus I, is a zero as well. So now I have 3 zeros. One is -1, the other one is 1 minus I, and finally I will have 1 plus I. So giving one complex solution basically means you have 2 solutions. And how do you find the function? Is you say f of x, again we assume the leading coefficient is 1. X minus -1 times x minus 1 minus I and x minus 1 plus I. What do you get as the product? You can multiply. I'm going to multiply these two first together because I have the formula for this multiplication. And it makes the work less. So I still have x minus -1 is basically x plus 1 times. If you multiply these two, what you get is x squared minus 2ax, which is minus 2x, and plus 1 squared and plus b squared, which is another 1. So you'll get plus 2. Okay, now again, if you multiply these two, what you get is exactly this parentheses. And now you can distribute x times that, x times the other one, x times that one, and so on. I just used that shortcut so I don't have to distribute too many terms. What you get is x cubed minus 2x squared plus 2x plus x squared minus 2x and plus 2. Finally, x cubed, this is f of x. Minus 2x squared and x squared, these two will give me negative x squared. Plus 2x and minus 2x will cancel out, and I have plus 2. This is the polynomial. You can check to see if those are really the solution. For example, the easy one that you can check is -1 a solution? Just replace -1. Figure out what is f of -1. It should be 0. If I replace -1, -1 cubed minus -1 squared plus 2. What do you get? You get -1 minus 1 plus 2. And we get 0. That shows that -1 is a solution. The same with 1 minus I and 1 plus I. It's going to be a lot of more work, but you'll get the fact that they are both zeros of polynomial. Okay, this is if you're given polynomials, finding a polynomial with given zeros. Again, this is important. If one of the zeros is a complex number, the other zero must be a real a conjugate of that. Okay, now we have space. Let me hold this up a bit. Okay. Using rational zeros to find all zeros of polynomial. We've discussed this already again. And if you remember, there was a P over Q. And we would say P is the depends on the factors of the constant. And Q would come from the factors of leading term, leading term coefficient. What was the P over Q? P over Q was the possible zeros of the polynomial. So if you, for example, if you're given this polynomial, let me erase this and call this f of x, and ask you what are the zeros of f of x. Is there a rational zero or not? And you don't see a way to factor this polynomial because it's a third degree polynomial. It would be harder. So what you do is first try to use the rational zero theorem. It means find out all the possible rational numbers that could be zeros of f. So create that P over Q and say, what are the possibilities for Q? Q is the coefficient of the leading term. In this case is 1. So what are the possibilities? It could be plus or minus 1. That's the only possibility. How about for P? The possibilities are the factors of -6. 1 could be a factor as well as -1. How about -2 and +2? Again, the denominator is only plus or minus 1 because those are only the factors of 1. Plus or minus 1 again. Plus or minus 1. Factors of -6 are positive and -1, positive and -2, positive and -3, positive and -6. These are all the possibilities to be zeros of f. You can simplify it. Every number divided by plus or minus 1 is just the same. So you will get either plus or minus 1. Now let me use a different color just to tell you that these possibilities are simply plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And then we would figure out one of these, hopefully, to be a zero of f. Okay, what would you do is you go through these numbers. For example, I'll pick 1. Through synthetic division, I'll say the coefficient of x cubed, x squared, x, and constant. These are the coefficients. -5, 8, and -6. And we're assuming 1 is a 0 at this point. We're checking to see if 1 is a 0. Drag down, you drag down 1. 1 times 1 is 1. Add them up, you'll get -4. Multiply -4. Add them up, you'll get 4. 1 times 4, 4. And here 2. This was the remainder. Since the remainder is not 0, I can say, okay, 1 is not a 0 of f. I will move on to the next number. You can try -1, you can try 2, 3, whatever. Pick from these sets of number. This is all the possibilities that could happen. What if we try 2? 1, -5, 8, 6, -6. Okay. Again, drag down 1. 2 times 1, 2. -3. 2 times -3 is -6. You'll have 2. 2 times 2, 4. What we get is -2. Again, remainder not 0, that means the choice of 2 was not a good choice because it's not going to be a 0. I'll move on to another number. Next number on the list, it could be positive 3. You can try negative 3. You can try negative 2. I'm going to try 3. I'm guessing it's not any specific way that I'm picking the numbers. I'm just guessing and go on. Start 1, 2, 3, 6. Then I'll go negative 1, negative 2, negative 3, and 6. Hopefully, I'll reach the solution fast enough. Okay, drag down 1, 1 times 3, 3. Add them up, negative 2. Negative 2 times 3 is 6. Negative 6. Add them up, you'll get 2. 2 times 3, 6. 6 and 6, 12. Oh, this is negative 6. There we go. There we go. 6 and 0. Yeah. Now I see a 0. That means 0 remainder, which means 3 actually is a 0 of the polynomial. So this is a 0 of the polynomial. If you replace 3 into the f, what you get is 0 as the result. So what can I do? Because I'm looking for all the zeros of the polynomial. So I can say f of x is basically x minus 3. This is one of the zeros. If you remember, if you divide by x minus 3, what you get is these terms. This is the constant. This is coefficient of x squared. Which means I have 1x squared minus 2x plus 2. Now, this is my polynomial. And if I set it equal to 0, what do I get is x equal to 3. What is the other solution? The other solution is coming from x squared minus 2x plus 2 equal to 0. And I will figure out just by using quadratic formula or factoring. In this case, I'm not sure if you can factor. So use quadratic formula. X equals raise this a bit. X equals negative b, which is 2 plus or minus square root of b squared 4 minus 2ac minus 4 minus 4 b squared minus 4ac minus 4 times 2, which is 8. There we go. Divide by 2. You can simplify it. X equals, therefore x equals 2 plus or minus square root of negative 4. Here's the 2i. Complex number shows up. Divide by 2. Which is, you can divide everything by 2. 1 plus or minus I. So I found the other two solutions. 1 plus or minus I and x equal to 3. These are the solutions to this specific cubic polynomial. This polynomial. It wasn't possible to factor it into 3 terms with real coefficient, but we factored it into 2 terms. One had real coefficient, the other one had complex solutions. And what were the complex solutions? You can look at the complex solution and say, okay, these complex numbers are conjugates of each other. If they're conjugates of each other, it should make sense that the coefficients of the original polynomial is a real value. Okay, this is nothing new. Everything is exactly the same as what we have done already. It's just I wanted to show you for complex numbers, the same process goes on. Okay, I think this is good enough for this topic because we've already discussed it with real numbers and stuff. Next time I will hopefully discuss inequalities for polynomials. I'm going to stop at this point.